Hello friends, you are watching Erudire Plus, the professional CAD/CAM solution provider. This channel provides basics of finite element analysis and computer-aided mechanical engineering design and analysis using CAD-related software. Let's get started.
Hello friends, today we'll show optimization of a CFD problem using SolidWorks Flow Simulation. In this case, we'll use a converging pipe for this optimization. Based on the velocity of the exit end, we have to optimize this geometry. Okay? And we'll be using SolidWorks software for this complete optimization and analysis. Let's get started. We're starting from parse. Starting from front plane, normal to sketch central line, let's put smart dimension to this one as 300 millimeter. Starting some lines, smart dimension from here to here equal to 250 millimeter, and from here to here equals to 150 millimeter. Let's make this length more, equal to 500 millimeter. Okay, now we can offset this one through 5 millimeter. We can join this part, and this extra part we can trim it out. Let this thickness be equal to 5 millimeter. So to make this drawing closed, so for that we can extend this one to little bit. The drawing is closed. To see the right hand side also. Trim out unwanted entities. Done. Let's see the complete drawing. Fine. Exit from the sketch. Select the sketch again, and features, revolve boss base with respect to central axis. We got the profile. This is the converging tube, right? Air will be flowing from this input end and it will be passing through this exit end. So in this case, optimization case, we have to optimize this geometry with respect to some exit velocity. Okay. Now for this CFD analysis, first of all, you have to make this object transparent. You can make it transparent. Select the object, then change transparency. Done. Object is transparent. Next one, we have to create the closed geometry. For that, list will be provided at the entry and exit points. This will come from Flow Simulation Tools, create leads. Leads can be provided at the surfaces only. Entry lead is made. Now we're at the exit point also to make the lead. It is done. Green check. Our geometry is ready. Right. It is an internal analysis. We can check the geometry is okay or not. Result is successful, so our geometry is okay. You can see that. Next one, you can see whether volume is generated or not. A solid volume is generated, so geometry is complete. We can start our CFD analysis. First of all, we have to save it. First of all, we have to save this part by the name of Converging pipe. The CFD environment will be started with wizard. The default name of the project is project 1. Next, we are selecting SI unit and pressure will be in, let's take the pressure as in megapascal, and we are considering up to 3 decimal places, and we can take temperature centigrade scale. Next, it is an internal analysis. Next, we have to select gases as air particles. Next, we are considering default parameters for these roughness and thermal conditions. Then finish. This is the computational domain, that means through which all the calculations will be carried out. We have to hide this domain part. Next, we have to apply these boundary conditions. For better application of boundary conditions, we can make the segmented view of this object. We can cut it from front plane. It's cut along the front plane. Now we can apply boundary conditions properly. Boundary conditions, insert boundary conditions. We want to apply a volume flow rate of, inlet volume flow rate of 1 meter cube per second at the entry phase. Done. Next one, another boundary conditions to be applied at the exit end. So insert boundary conditions. At the exit end, we want to apply environmental pressure. So select that exit surface. Okay. Both the boundary conditions have been applied perfectly. Now we want to see the complete object. This is the model, right? Next, we have to apply some goals. Insert surface goals. We can have a lot of goals, but our aim is to have optimization of velocity at the exit point. So we want to see average velocity at the exit surface. Okay. Goals. Insert surface goals. We want to have average velocity at the exit surface. So select other and lead number 1. Okay, we have only one goal, and based on that goal we have to optimize the geometry. Okay, then let's run it. Solver window, we can see it. It started calculation and solver is finished. We can see the results. We can see different cut plots and also flow trajectories, but this is not our goal. Our goal is to optimize this geometry based on some specific output, right? So directly we will see the results. We are not bothered about this flow trajectories and cut plots. We will see the goal plots. Insert goal plots. We have only one goal plot that to be shown right now. Our goal is, you can see the velocity at the exit surface equal to 2.78 meter per second. It is very less velocity. So our aim will be to make the velocity some specific value equal to 10 meter per second. Based on that, we have to change some dimensions or some input values. Okay. Now we have to go for optimization. So starting optimization from solve, new parametric study. We have a lot of parameters, input variables and also dimensions for this optimization. We'll select only one input variable. Let's select the dimensions from here itself. Let's select the exit diameter 150 mm. Our aim is goal optimization. For that we have selected the exit diameter 0.15 meter. That can be varied with a specific range. We can edit the variation from 0.05 meter to 0.15 meter. Within this range we have to find that velocity at the exit point. Next one, our criteria. This criteria will be based on our goal. Select the goal. We have only one goal, average velocity at the exit surface. Select that one, and the target value should be provided right now. Our target value is to have a velocity of 10 meter per second and with a variation of 0.1 meter per second. Let's see the scenario and run it. It's calculating. First calculation is done. Target value was 10 and it has got 2.78. Lot of iterations are going on. With second iteration we got the target velocity equal to 24 meter per second. Third iteration we got 4.6 meter per second. Is going on changing again and again. By the same time the dimensions of the geometry is also changing. By the same time we can see how much is the deviation from actual geometry. Fourth iteration we got the value of exit velocity equal to 7.9 meter per second. Iterations are still going on. Solution is already converged. Now see the results. Out of 10 iterations we can see the last iteration we can see the output velocity at the exit surface equal to 9.94 meter per second and our target velocity was 10 meter per second, which is having deviation of 0.05 meter per second. So we have achieved the goal. To obtain this goal we had to fix the diameter as 0.786 meter, that is 78 millimeter, right? So 78 millimeter diameter at the exit surface will provide a velocity of 9.94 meter per second, right? And this is a very basic example for optimization of CFD analysis. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.